What's up guys, it's Aman here with another video. In today's video, I'm going to cover 5 astrophysics terms that you hear in the neighborhood, classroom, dinner table, or just society in general. Let's get started. Alright, so redshifts and blueshifts all have to do with light and its wave phase. Now, light can be a particle too. So essentially what a redshift is that if you have an object that emits light, and that, like a star or a galaxy, and that object is moving away from us, then its light waves, per the Doppler effect, will be perceived as longer than they actually are. Now, if a light wave becomes longer, then it's moving to the red end of the visible spectrum. So the light waves of that object look red, hence the term redshift. A blueshift is just the converse of that. If a light-emitting object is moving towards us, then its light waves, also per the Doppler effect, will shift towards the shorter wavelength end of the spectrum. Now, the shorter wavelength end of the visible light spectrum is the blue end of the spectrum. So its light waves shift to the blue end. They're perceived as blue, hence the term blueshift. Astronomers can analyze emitted light spectrums of celestial objects, like distant galaxies or quasars. Spectrums dominated by red or shifted towards the red end indicate an object receding from us, whereas spectrums dominated by blue and shifted towards the blue end indicate an object moving towards us. The expansion of the universe is a difficult concept to grasp. In essence, our solar system is a part of the Milky Way galaxy, and there are several other galaxies like ours and much larger than ours in the universe. For complicated reasons, our universe expands. There's no really end wall to the universe where you can go and say that this is the edge of the universe and this will be the edge of the universe forever. Now, this expansion of the universe means that everything in the universe is constantly moving away and receding from each other. As the universe expands, the distance between galaxies or celestial objects increases. And this is the premise behind Hubble's law, that recessional velocity, the rate of recession, is directly proportional to the distance between two cosmological objects. Now, a light year is a unit. Now, the biggest misconception, probably because of its name, is that a light year is a unit of time. But that's really not the case. A light year is a unit of distance. It's the distance light, that super fast wave particle, travels in 1 year. And since the speed of light is just extremely fast, the distance that light covers in 1 year is absolutely huge. That distance is actually just short of 6 trillion miles. We use light years to determine how far objects are. For example, the star Sirius is 8.6 light years away from us, which actually makes it a pretty nearby celestial object. So that means that the light that travels from Sirius takes 8.6 years to reach us, which means that the image we see of Sirius created by the light that travels to us is outdated by about 8.6 years, that image is. It also means that if we were to travel to Sirius at the speed of light, it would take us 8.6 years to reach there. Most celestial objects that are well known, it would take you about hundreds of thousands of years to reach them, so we're probably not going to any celestial objects nearby soon. A supernova is an exploding star that is an absolutely beautiful sight to see. Now, many physicists are currently researching supernovae to get a better picture of them. The way it works on a basic level is like this. So a star runs, lives, and produces energy off of nuclear fusion reactions. When the fuel for those nuclear fusion reactions runs out, well, that's not exactly good. Running out of fuel for the nuclear fusion reaction means that the star is going to evolve. And if the star is massive enough, it will evolve in such a way that it will explode into a supernova. An exploding star sounds very dangerous and scary, and it absolutely is. If the strongest supernova were to come within 3,000 light years of Earth, it would disrupt atmospheric conditions in such a way that it could wipe out most of the life on Earth. Now, luckily, we haven't had, nor do we foresee, anything of that sort of strength coming near Earth, so we'll be fine. Now, the Sun is a very big star that's near Earth, so you might wonder if the Sun will ever explode in a supernova. Will it ever go, boom, supernova, bye Earth? Well, the answer is that you have nothing to fear. The Sun is not nearly massive enough to supernova, and when it runs out of nuclear fuel in a few billion years, it will just turn into a red giant and vaporize all of Earth. So we don't have anything to fear at all, not a problem at all. Black holes are these really mysterious warps in space-time. Black holes are also due to stars running out of nuclear fuel and evolving. If a star is really large, like I mean really large, then when it runs out of nuclear fuel, it can go into a cycle in which it turns into a black hole eventually. So black holes are these regions of intense gravitational attraction and pressure. It's small, but it is very massive, which means it's very dense. Now, a common analogy is that it's like you're fitting the mass of a skyscraper into an atom. That's how much pressure, that's how dense it is. If you get anywhere near the event horizon of a black hole, that's the region from which there is no escape, the immense gravitational attraction and pressure will suck you in. Now, once you're in there, you will be what astronomers call spaghettified. You will be stretched into these thin strands because of that immense gravitational attraction. Black holes suck in and destroy countless planets, stars, and cosmological objects that get too close to their event horizon. Now, there are some questions on the role this might serve. Maybe this even helps us here on Earth. Does it kill out our competition, and maybe it's cleared the way for life here on Earth? Black holes are categorized into different categories based on their strength. The strongest black hole is called a supermassive black hole. And there exists a supermassive black hole at the center of every galaxy. So maybe supermassive black holes are necessary for galaxy formation. There is a supermassive black hole at the center of our Milky Way, the galaxy we live in. And if you even get near that supermassive black hole, you will be sucked in. All right, folks, those were the 5 terms to know. Hopefully you found these brief explanations helpful. Don't forget to like and subscribe, and in the comment section down below, let me know which term, which concept you found most interesting. Well, I will see you in 1 week, but if not 1 week, then 2.